Hi everyone. So as you can see here, my project in image processing is about optimization of image registration by uh, Lucas-Thomas algorithm. Uh, my name is Deepak from University of Florida, and coming to the contents of my project, as you can see here, it mainly consists of 6 of them. The first one is the introduction of my project, then description of the algorithm, then evaluation of the algorithm, and then we'll discuss about the code and conclusion and the related work based on my project. So moving on to what introduction is, as you can see here, image registration is a very important task, or algorithmically a very important method to be used for many different applications. As you can see here, there are two images side by side. The left image is a little lighter than the right image, um, or to be precise, the right image is a little darker than the left image. So the difference between the two images is pretty minimal, which can barely be seen by our naked eye. But this shouldn't be the case, especially as you can see, this is a CT scan, which shows the growth of the tumor, uh, and the right one has more details than the left one, which implicitly means that the right image the tumor is a little larger than the left image, but it cannot be said by our naked eye. But that's why we can use the image registration algorithm to find the differences between the two images, which is not direct math. It takes an image registration algorithm to understand the difference between the two images and figure out what the growth of the actual tumor is. Now, as you can see, this block diagram really explains what a registration problem or an algorithm is. As you can see, in every registration problem, there are mainly two input images, which are basically the same image or the same frame, but taken at different times. So there are very few features that differ from the first image and the second image. So initially, what registration algorithm actually does is a bank of Gabor filters filter the image 1, and then try to find a local phase difference with that of the filtered details of the image 2. So the local phase difference between the two will be used to determine the local translation estimation of the entire registration. And once we find what local translation estimation is, we can try and solve for the registration parameters, which basically tries to find out the displacement of the feature points between the two images. And as we discussed in the last slide, it can find the size of the tumor or increase in size of the tumor, to be precise. And now moving on to the next slide, this is what I actually implemented in my project. This is called the Lucas-Thomas algorithm, which is basically a feature tracker. Um, as you can see, the input image is given to the algorithm, then some of these feature points are selected from the input image and they are saved until the second image comes in as a second input. There are two possibilities now. The second image has some feature points saved first, uh, which might contain some lost feature points. Lost feature points is nothing but the feature points that the algorithm is expecting from the second image, because it's all already in the first image. But since the second image is taken at a different time, all the features may not exist in the second image as to be existed in the first image. So once the feature points are detected, it searches for the lost feature points and deletes them if there exists any. So once the lost feature points are deleted, these tracked points are saved. So a tracking point is something we usually track within a sequence of images to find out the displacement between the tracking. And as we discussed in the previous example, the tracking point should be somewhere in the middle of the tumor to find the distance from the image 1 to the image 2 with respect to the tracking point. So this is what happens in our algorithm. Next, so moving on to what KLT Thomasy tracker in our algorithm really works. As you can see, the frame 1, we have a tracking point in the middle of the screen, right around our origin, if we consider an axis, I guess, a two-dimensional space. Now, when coming to the frame 2, which is the second image, or the frame 2 of the image we take, it moved towards the fourth quadrant at somewhere around a 45-degree angle. The same thing happened with the frame 3, which moved even towards the right, and the process continues until all the images in the sequence are over. As you can see here, the leftmost image represents the total tracking of the tracking point of the image sequence. As you can see, is somewhere around a 45-degree angle onto the first quadrant. So this is what a KLT tracker actually does. It tries to track the tracking point such that you can find the displacement of the tracking point and figure out a result of image registration. So moving on to what my code actually does, as you can see here, we try to derive, or I try to make a filter which uses the weighted sum of the middle pixel the most, and then give it a tracking point which moves to the right as suggested in the previous slide, and it must match the filter size for computation of temporal derivatives. And then once we get the image sequence, this image is the input image, yos.10.pnm is the input image, and then the input parameters are read into n frames, and the motion sequence is observed, and we displayed our first sequence here, and then the color map is gray. And what my code actually does after this is try and find out the derivative in time. So the derivative in time is found, and all the pre-filters in the other directions are found. As you can see here, the convolve function, what it actually does is it combines two images, or two matrices to be precise. These matrices are nothing but a set of parameters that represent an image, or a set of parameters that represent a pixel. So once the convolution function is observed, we can try and find the show flow field, which basically means that the flow of the tracking point is towards the right, or whatever the tracking point moves, if a different image is selected. So moving on now to what the code actually does, let's take a look at our code here. So as you can see here, this is my code. If I run this code, as you can see, the image, or the image sequence, is run for a sec there, because there are only 3 images in my sequence, and the 3 images have 3 different scaling, and the final output image has all the blue dots on it, which basically means the displacement of the tracking points, or displacement of the features to be correct, and these blue lines represent what how much the feature points from the first image have moved when we came to the last image in the sequence. So this is what we try to find here, the displacement of the tracking points from the first image to the last image using the Kennedy-Lucas-Thomasy algorithm. So going back to what my results are, as you can see here, there are the first image on the left and the last image on the right. So these two images, we can clearly observe that they are different in a way or two, but not that much, because these two are the same frames but at different times. So you can find the displacement of the feature points represented by blue dots or blue lines. And now let's move on to what my project really tried to prove here. So the conclusion of my project is that the KLT algorithm proved to be giving the feature tracking results just as expected, and it gets a very low pixel error, which is a major discovery, because 0.6% doesn't make a lot of difference if you're trying to find out uh, what a tumor actually grew, or a limited time, because 0.6% doesn't really matter if you're not dealing with microscopic objects. But as long as you're dealing with normal images, 0.6% is okay to get. Then I also figured out that it is faster than other feature tracking algorithms, and it usually is much more economical than conventional feature trackers. That I think is one of the greatest advantages of KLT algorithm. So, and also my optimization improved its speed significantly. My optimization usually uses a Newton-Raphson method for minimization of the epsilon L value, which basically represents the displacement value. So this is how I think my KLT algorithm really concluded. Then coming on to the related work, as you can see, uh, the KLT algorithm can be used in medical imaging, as we discussed in the first example. Then it can be used in geosatellite imaging for finding new foreign bodies or new objects in the space with a fixed frame ratio. And then it can also be used in pattern recognition, in machine learning, in surveillance. Mainly the surveillance is CCTV footage, so the images might not be clear, but still KLT algorithm does a good job with just a 0.6% pixel error. So that finds out very minute changes in between the two images of the same sequence. So I think KLT algorithm is a pretty good feature tracker, mainly because it's economical and it does well with uh, normal images. So I think this basically winds up my project. So thank you very much.